Hi, welcome back. After having seen Noether's theorem and the conservation of linear momentum and angular momentum, it is time to explore conservation of energy. Let's consider the following quantity. H equal to the sum of the partial of the Lagrangian with respect to q dot sub I times q dot sub I minus the Lagrangian L. This quantity, just as the Lagrangian, has units of energy. I'm going to calculate its time derivative. To do that, I need to be aware that the Lagrangian depends on qi, q dot I, and t. So the derivative of the Lagrangian with respect to time is the partial of L with respect to q times the derivative of q with respect to t plus the partial of L with respect to q dot times the time derivative of q dot plus the partial of L with respect to t. With this in hand, I write the derivative of h with respect to time. First, it is the derivative of the product, and then it's the derivative of the Lagrangian. But look that the first and third terms cancel, and the second and fourth terms also cancel, so the derivative of h with respect to time is the negative partial derivative of L with respect to time. This means that if the Lagrangian does not depend explicitly on time, this new quantity h is conserved. This h will be conserved if the Lagrangian depends on the positions and the velocities, but not explicitly on time. Now the question we have is, who is h? Well, let's write it in Cartesian coordinates. L is the kinetic energy minus the potential energy. So h is, from its definition, to be the energy of the system. So if the Lagrangian does not depend on time, the energy is conserved. So h is the energy so long as the Lagrangian of the system describes a closed system with no external forces involved. If the Lagrangian doesn't represent a closed system, h will be conserved, but will not be the energy of the system. Let's see this in an example. Consider a bead on a stick that rotates on a horizontal plane with constant angular velocity, omega. The kinetic energy of the bead is written in polar coordinates. There is no potential energy here. The quantity h is then because the Lagrangian doesn't depend on time, h will be conserved, but this is clearly not the energy. There is an external force pushing the bead which is not represented in the Lagrangian. This force causes work to be done on the bead, increasing its kinetic energy. Let's apply Lagrange equations with Lagrange multipliers to find this force. The constraint here is that F is equal to theta minus omega t minus theta dot equals to 0. With theta dot equal to omega and theta 2 dot equal to 0, then the equation of motion is mr2 dot equals to mr omega square. This is Newton's second law in the radial direction, ma equal to the centripetal force. And the constraint equation is lambda equal to 2 mrr dot omega, which is Coriolis force, a fictitious force result of the system being in a non-inertial reference frame. This force is on the theta direction as the constraint depends on theta. So it is the tangential force. May the science be with you.